In today's video, we're diving into the structure and properties of two important allotropes of carbon, diamond and graphite, while we'll be covering other fascinating forms like graphene and fullerenes in the next video. But first, let's clarify what an allotrope actually is. Allotropes are simply different structural forms of the same element that exist in the same physical state. So when we talk about carbon in its solid form, it can take on a variety of structures including diamond, graphite, fullerenes, and graphene, all of which are allotropes of carbon. Now, both diamond and graphite are examples of what we call giant covalent structures. This means that they are composed of a vast number of atoms bonded together in a repeating, regular lattice by strong covalent bonds, which gives them both impressive strength. In the case of diamond, each carbon atom forms 4 covalent bonds with 4 other carbon atoms, which is the maximum number of bonds a carbon atom can make, creating a tightly packed, three-dimensional network. While you're not expected to draw this complex structure, it's important to recognize its rigid and orderly form. Because each of these bonds is extremely strong, breaking them requires a significant amount of energy, which gives diamond its legendary hardness and incredibly high melting point. However, diamond does not conduct electricity since it has no free electrons or mobile ions that could carry a charge. Now, if we compare these properties with those of graphite, we begin to notice some key differences. Each carbon atom in graphite is bonded to only 3 other carbon atoms instead of 4. These atoms are arranged into hexagonal patterns, forming flat sheets. These sheets are then stacked on top of one another in multiple layers, but here's the interesting part. The layers are only weakly held together because there are no covalent bonds between them. As a result, the layers can slide over each other quite easily, making graphite soft and slippery, especially when compared to diamond. That said, graphite still retains a high melting point due to the strong covalent bonds within each layer. You might remember that carbon can form up to 4 bonds, but since each carbon atom in graphite only forms 3, this leaves 1 electron per atom unused in bonding. These unused electrons become delocalized, meaning they are free to move through the structure. It is these free, delocalized electrons that allow graphite to conduct electricity and heat, a property that diamond does not share. Before we wrap up, it's worth noting that a single layer of graphite is called graphene. Scientists have managed to isolate these individual layers, and from them, they can create fascinating new carbon structures such as hollow spheres and nanotubes, which are known as fullerenes, and we'll be exploring those in more depth in the next video. That's all for now. We hope you found this breakdown useful. If you did, don't forget to like, subscribe, and share it with others. We'll see you again next time.